Hello, everyone. I'm Balaram Sarkar. I'm a master's student at Indian Institute of Technology, Indore. And here in the AI lab, we have been doing research on speech-to-text translation. So to show you the roadmap of our experiment, I'll be talking about the introduction in the beginning, the motivation behind our work, the previous methods used in this field, and what exactly is the modality gap we're talking about in this topic. What is the methodology that we have been using, the data set, the experiments, the result, and the conclusion work. So to say about what is speech-to-text translation is to have an audio speech in one language and translate it into a text format in different language. So previously, the older methods which did this task were doing following a cascaded system, which involved first using an ASR system, which transcribed the audio into the same language text, and then to use a machine translation, which further translated the text from source language to the target language. So this is the older method, and the latest or the current method being used is the direct approach, where we don't need any intermediate stage in between. So the source language audio is directly translated into the text format of the target language. So I'll be saying about the motivation behind our project is being from India, which houses over 20 language regions where more than 20 language are being used, not only as a regional language, but even as an official language of that state or region. So there is a huge language barrier gap between two different states or geography. So the motivation behind our project involves this, as speech-to-text, as even normal translation can be used in many various fields for overcoming the language barrier gap. So we know about the famous mathematician A.K. Ramanujan. So we don't know how it would benefit even more if we had some if he was exposed to the rich knowledge and education available over the internet, and especially for, let's say, the online lectures or any videos available in YouTube and etc. So not only in this field, but even for communicating with the rural underprivileged children, and even the villagers, for not only in the domain of education, but health, and even for other use cases. So this basically was our main motivation, and the motivation keeps on increasing even by hearing yesterday about Professor Alex's journey since the 90s on this field as well. So these are the main baselines that we've been following. So the previous ones since 2018, having the ESP-net, the newer ST, the XST-net, and the FAIRSIC, all these methods were using the normal way of speech-to-text translation, where the input was the source audio, and the output was supposed to be the text in the target language. So the modality gap that I've been talking about is the one, the first paper, which says on ST, that is contrastive, cross-modal contrastive learning method, which is being used for bridging the modality gap also. And we'll be talking about what are the advantages of our method regards to this one. So what is this modality gap? So when we have a speech and its parallel transcript, as we can have an example in this diagram, we say the yellow circles are the speech, and the triangle pink are the text resembling that speech. So in a normal representation, when we have the embeddings plotted in the vector domain, we can have like, there is a difference in distance between them. So we have the speech and the text having a lot of distance between them because they belong to different modes of data. So speech is a different mode and text is a different mode of data. So hence the distance. And the speech to text, or rather the translation system in a whole, would perform better if these were aligned, these two different embeddings, or these two different features of speech and text, they were aligned together. Now, they has to be aligned, but it has to be taken into consideration that the positive features, which means that the speech and the text are having the same meaning. So it has to be mapped closer to each other. And the negative pairs, which means that the speech and the text having dissimilar meaning, it has to be mapped further away from each other. So this is what is called bridging the modality gap. So previous methods have also been trying to do this. This is just saying the same thing. So the previous methods have been trying to do the same thing, but they had to label the data as this is the positive and this is the negative, and which became computationally more expensive because there was negative mining, negative sample mining involved. And plus they required a huge amount of data for effective training. So before I lead to the proposed approach, I would talk about the SimSiam. So the full form is Simple Siamese Network. So this was coined in 1990s, where it was firstly used to match signatures. So is the signature having like, is it an original signature of a person, or is it someone trying to make a fake version of it? So it was used for that purpose. So, and with the development of neural networks, this gained a huge popularity, because nowadays it has been used for many different tasks, and especially for face similarity application. Here we can see that the face having the same persons, two different pictures having the same person, is giving a high similarity score, and different persons are giving a low similarity score. So this is about the SimSiam. And one limitation it has is that the model learns to output the same representation for all inputs. So this this is what it's called, the model being collapsed. So when this happens, there is a small component in this system, which is the stop gradient. So it stops the gradient from one network to not update the weights of the whole system during the time of backpropagation. So this prevents the collapse, and it helps the model to learn better representations from the network which is required. So we tried to use this mechanism in our whole approach to bridge the modality gap. So on one side, we have the speech input, and one side we have the text input, and we have the speech encoder and the text encoder. So this brings this outputs representation, which is having a more meaningful features of both of them combined. So it will have the ideal representation that we talked about. So, and this doesn't even involve for us to label the data or say that it is we are feeding a positive sample or a negative sample. So we just give the data as it is. And so without the need for any mapping, we are able to determine if it is a positive sample or a negative sample. Hence, it saves a lot of computation. So this is the first stage. And the whole pipeline is, first we train the SimSiam network, and which is like an unsupervised framework. on the unlabeled corpus that we have, and to learn the speech and text representations, the aligned representations. And then further, we use these representations to by using the and we perform the speech to text translation by using the speech to text transformer model. From the framework we have used is FairSig by Facebook. And then further, we use this model to practically use on any languages that we've been training it for during inference. So here is the whole process, how it is happening. The data set is having a triplet. So we have the speech, the translation, and the transcript as well. And even though we didn't have the transcript, we could even use an ASR data for the first task for the for bridging the modality gap. And then we could use that representation if we had the translation for the next, which is to have the speech to text translation, the second stage. So this is about the model. The data set that we had used is the largest available public data set available for speech to text translation. It is the MUSTC data set. It is comprising of TEDx talks, and when it was first launched, it had 8 different directions. So for example, English source audio to parallel text in 8 different European languages. And so we had considered using 4 languages for our experiment, mainly the German, French, Italian, and German, French, Dutch, and Italian. So these are the details of the data set. And these are the details of the components that we have used for SimSiam. We had the speech encoder was CNN and wave2vec. The text encoder was a BERT-based uncase. So the loss for the SimSiam training was cosine similarity loss, where it calculates the cosine distance and to give a meaningful representation for both of them by calculating the overall distance. And for the S2T translation, which is the speech to text translation, we use the framework given by FairSig S2T transform model, which is also a toolkit, which is where we can implement, which is a research platform for implementing ASR or machine translation or speech to text or any NLP related projects. So we use that. And so the details for the transformer were as below. We use 6 encoder decoder layers and 8 attention heads in each layer. The architecture was 512 hidden units. The loss was label smooth cross entropy loss with a label smoothing factor of 0.1. So coming to the first section of result, we see, so the first experiment was to bridge the modality gap. So here we have before training and after training images of the distance between a positive pair of sample and a negative pair of sample. So the positive pair of sample are the ones which had the speech and text having same meaning, and the negative samples are the ones in purple, which has the speech and text in which has dissimilar meanings. So initially, the model was not able to detect any change, or they were not able to identify which are the positive pairs or the negative pairs. But after the training, it forms different clusters. We can see that the distance between the positive pairs are less and the negative pairs are more. So this is, it shows the effectiveness of the training. And for the second experiment, so in combination of both these, the speech to text translation along with the modality gap bridging, we see that the baselines of using different models previously translation. So it showed like the average accuracy in blue, it's greater than all the other baselines, and especially the honesty, which has been also doing the same task of modality bridging, but where the negative sample mining was making the model even more complex in terms of complexity or cost. So whereas our model, we do not need to mine any negative sample, and hence it not only gives same but even more blue, but in terms of time and cost efficiency, it is better. So these are the results for these languages. And finally, we see that even when before training in the vector domain, where the speech and transcript were far away from each other, and I don't know if it is properly visible, the red dot being the transcript and the blues being the speech. So after the training, they overlap each other, which means that the training of the modality bridging experiment, it shows its effectiveness. So it works in that way. So these are the features for speech and text, and we see that they overlap each other after the training. So I come to the conclusion with this slide. So we have trained for two different small experiments. Firstly, for the similarity learning, in which we use the SimSiam network to bridge the modality gap and to learn more better representations of speech and text data together. And we further use it for developing speech to text translation. We leverage the SimSiam network, and we see that the results on the data set, the MUSTC data set, shows the proposed method indicates, it shows the effectiveness of the proposed method as compared to the baselines. And along with that, I would like to say that for future, I'm also developing the big data set as MUSTC for Indian languages. So we can try to incorporate more dialects or scripts if there are any. And we'd like to see how this method works on them as well. And we would also try to we try to experiment on some other methods to see if the modality bridging techniques get better or not, with some other tweaks to the whole model. And along with that, we can also, one experiment that we haven't performed yet is to see if adding an ASR data to the first experiment, which is to bridge the modality gap, will actually strengthen the whole process of speech to text translation or not. Because more than speech to text translation corpus, we have ASR corpus in, So we would definitely like to see if it is of any help to this model overall or not. And finally, we wish to have a model which is capable of being trained continually. So firstly, we have the model to train in English to, let's say, German, and then the same model without any other previous language training, we could train it on some other, let's say, English to French. So in a continual fashion, we have, without the need to preserve the previous data set or any other complexities, to have this. So these are the future work for our experiments. And hereby I end my presentation. Thank you.